know that. Okay. uh, Today's current treatment planning systems are commercialized by international companies, and they are usually quite expensive software. And apart from that, they are black box system with low modularity and often limited access to the code. This means that research is only possible by means of collaborations and often with non-disclosure agreements. When it comes to research, the problems we have is that we might have delay in research, or at least more difficult situations when we want to use this TPS for research. And they also impact industrial implementation and clinical evaluation of new techniques and prototypes. So two examples here, but of course we can give many. It's the proton R therapy, which started already several years ago, and it's currently in research, and a lot of research in treatment planning is needed for this new technique. And another easy example is flash radiation therapy, either with protons or other techniques. And that also needs a lot of research in treatment planning, right? So current existing solutions that are many out there, but two of the most well-known are MATRAT, which is based in MATLAB, and they are out there since 2015, I believe. And then SER, which is much older, and it's also very well known. There's also Slicer RT, which is very well known. But we thought that there was still room for another solution. And I have to say the particularity of OpenTPS is that it's based on Python. We thought that there was no tool in Python when we started developing this in 2021. So that's why we started developing, and it's very like MATRAT actually, but in Python, so it's open source, and it's designed to have high modularity, easy to use, and that can be used for prototyping. So Sophie will explain later. We have separated the graphical interface from the core code so that people can use it easier for scripting too. So it's really made for research. And with that, we want, of course, to accelerate research collaboration, and of course, as all want, improve cancer treatment and standard of care. So I thought it was a bit nice to tell the story of our tool, OpenTPS, but also of our lab, because all the knowledge today in OpenTPS is not from a few months, it's from a few years. So we started in 2007 with ImReviewer, which was based on MATLAB, and it was just a platform developed by John Lee for PET segmentation mainly, and also image processing. Then Edmond Stepan started to work on Monte Carlo simulation. He did TomoPen for photons, for tomotherapy. But then we keep working on Monte Carlo also for protons. OpenRegi, it's currently used today also. It's also in MATLAB, and it's for image processing in general, with registration, the formal registration, motion management tools, etc. And then, as I said, in 2016 and 2018, I started working with Kevin, and we had two tools, MC Square, which is very well known today in pencil beam scanning proton therapy, and it's a dedicated Monte Carlo for that. Many people use it as secondary dose calculation too, and many people also for research. And then MIRO, we watch a robust treatment planning system also in MATLAB, coupled with MC Square. So that was the tools we developed back in time in MATLAB. But then we decided in 2021, Kevin started with that during the pandemic. Before moving to IBA, he's working now in IBA, and we started with OpenTPS, which is mainly a copy of what we have from MIRO and MC Square, but in Python. So the main tools we have, apart from the image processing, is for proton therapy. And so who are we? So as I said, this started in MIRO, But then, because we have a channel through IBA, there is also, we have very good collaboration, and then there is people in IBA, of course, interested in OpenTPS because of the proton therapy part. And there is also a lab in UC Louvain called PyLab, which deals more, not the treatment planning, but also image processing algorithms, and they are the IC team. So that's our team, and our users today are starting to grow. You are one of them. I know you are using for some research in Flash, and also some people in Raptor. Luciano, that I learned that is also working with you now, is working on that for photons. We have some slides later for that. So that's on my side.
Yeah. So now I will give you more a technical overview of OpenTPS. So as Anna said, the spirit behind OpenTPS is that it's a research TPS that was built by researchers and for researchers. And so the main features that you can find in OpenTPS are of course, everything related to reading and writing output. So many DICOM import-export tools, but also MHG to read CT, RT-dose, RT-struct, RT-plan. We have also all the imaging processing tools that you can find in OpenRegui have been rewritten from MATLAB to Python and integrated in OpenTPS. So image registration, segmentations, etc. And then we have the proton dose calculation written by Kevin Souris, which was written actually in C, but integrated as a compiled software into OpenTPS. And finally, we have also integrated, obviously, it wouldn't be a TPS without a proper optimization for proton therapy treatment planning. And we have also featured to make a robust optimization. And we also decided to make a friendly graphical interface because we know that medical physicists are not always programming skills. So it's also nice for them to learn to use the tools for their research without having the tedious programming behind. So yes, we already mentioned it, but MC Square was built before OpenTPS, so it's fast Monte Carlo simulation for proton PBS, and it's good to recall that it had undergone like 3-stage publication. First, the development of the tool itself, then it had been validated and compared to actual data. And of course, now the later paper that have been published with the tool are applications that are using the MC Square tools. And it's also good to mention that this tool has been integrated in research, right, in OpenRegui, MIRO, OpenTPS, but also in clinic. For instance, IBA dosimetry has integrated this dose calculation in their software MyQAIAN. And yes, so you can compute dose, but also LET, LET dose calculation. So the big feature of OpenTPS is that it's divided into main parts. We have what we call the core library, and then we have the GUI, so graphical user interface library, and it's well separated, such that the core library works independently from the GUI. So what does it contain? It contains all the data classes, so the CT object, RT plan, the region, the contours, the CT calibration, beam model, etc. Then we have all the IO tools for DICOM, MHG serialized, and obviously everything that has to do with data processing, segmentation, registration. And finally, what usually interests everybody also is the RT application. So everything we can build with the data classes, etc. So those computation, plan optimization, etc. And then we have the GUI. So we say that it's a standalone GUI because it's like, so you can launch the GUI and work without actually modifying the core library. everything that there is like some function to already optimize, design the treatment plan in the GUI, but obviously it's simplified. So if you want to use odd functions like more exotic one or that are implemented in the core but not in the GUI, you will have to link this somehow to the GUI, or we have also a scripting like in the GUI there is also a scripting tool that you can use to use the core methods. And obviously in GUI you find all the data visualization for the CT, dose, DVH. We'll see an example demo later of that. And yes, I want to emphasize that we really separate the core from the GUI. The reason is that sometimes, usually, at least most of us in MIRO, we work on the core library. We develop all of our research mainly in the core because we don't have time to implement, unfortunately, the GUI visualization tools. We try our best. But usually, sometimes we want to make like very heavy computations, right? And we want to do these computations on servers like clusters or cloud, and the GUI cannot run usually on this kind of server applications. So that is why we wanted something separated so that we can use the core independent from the GUI. And also, no, I think that's it. Sorry. Yes, PyQt5. Okay, so the GUI is structured with four main modules. We have the I/O, we have the data visualization tools with all you can display the image, the dose, the contour, profiles, and DVH. Then we have a few tools on the GUI that can be used to crop, resample, to adjust the window level, and also to use a crosshair to get to a slice in your image. And finally, we have made some panels to optimize the plan and compute the dose with MC Square. And we are using iterative solvers such as the basic one, gradient descent, but also more advanced ones such as BFGS. And we have also integrated linear programming, but for that, right now, you need a license because it's use Gurobi library. So this is what it looks like. So it's a screenshot of the GUI. So what we can say technically is that all the layout, widget, menus, and buttons, they are built with the PyQt library, while the profiles and DVH, they use PyQt graph. And finally, for image visualization, we use the VTK library, which is more tricky to use. Another point is that the GUI is mainly divided into three main packages. So we see the panels here on the left, patient data, ROI, plan design, blah, blah, blah. And then we have the tools that I've mentioned. So here you see, for instance, that's the crosshair. And then it's the luminous, the contrast tool, etc. And then finally, obviously, the viewer package here. Now let's talk a little bit more about the core of OpenTPS. So as we said, it's for prototyping, fast prototyping. We wrote in RT, but right now it's in PT. At least the code that is implemented online and available is for Proton. So it defines, as I say, all the data classes, algorithm, methods. It does not depend on the GUI, and it can be used to build application script that whatever you can imagine in a treatment planning system. And here are the data classes. So we talked about the CT calibration, the images, BDL, the plan, and other data. As you can see, there are many data classes. You can create your own. And here is an example. So here is the CT image object, which inherits from an image 3D with an origin, spacing, image array, or rotation, which itself inherits from the patient data to give it a name and associate a patient to it. So then another package in the core is the IO. So here, for instance, it helps to load the DICOM data. So you see we only use this load data function, which will load any data that OpenTPS can support. And then once you know what you want to get, for instance, here you want something of the type CT image, you get that data of that type, and you will get your CT. And here on the right, it's another example where we read a CT calibration in OpenTPS, and then we can rewrite even obtain the on-field unit for water, for instance, by using these functions that are specific to the for a CT calibration object. And finally, I guess it's the main interesting module is the processing modules. This is where all the interesting science happens, because this is where you will find everything related to those calculation, image processing, plan delivery, plan evaluation, plan optimization, registration, segmentation, etc. And I encourage you to go and check the example folders in which we have made, we have written quite a few examples associated to each of these category of research, it's a feature of OpenTPS. So now it's a quick GUI demo. So I put it in twice speed. So here we'll just load the patient. That's the interface. So the patient is anonymized. We can just drag and drop the CT. Then here we can adjust the window level, as you can see. We can set preset to see like a specific structure, like to emphasize some structure in the patient. This is, then it comes back to the other CT here. And we will display a dose. So here there are 4 individual doses because there are 4 beams, but the 5th dose is the total dose for this head and neck plan. So here's the full dose that is displayed now. We can also display the different contour. You can then display the DVH on the right of any ROI you are interested in. The body, for instance, here also. Then here is the plan design, a panel, as you can see. Here is just showing an example that we can use a tool to crop the CT inside the GUI. And then so here back in the plan design, you can adjust the spot spacing, layer spacing, the gantry angles you want to specify, couch angles. You can also modify robustness settings and so give setup, range error. You create the plan, and here is the plan optimization tab. You have this objective panel that you can use, and you can also use templates. So here it uses one. And you can define weight, minimum objective, max objectives, and I think now there's also the mean objective. And then once you are happy with your objective list, you can run the optimization. You have also this dose computation tab that you can use to perform a final dose calculation with MC² once the optimization is done. The optimization will now is comparing is showing a tab where he compares two different doses, so it's also nice to display this kind of things. So it's really like tools to help you visualize your results basically. But yes, it can also actually make an optimized plan in the interface. Here is showing that we can also show dose profile. So it's just drawing a line on the dose, and you see on the right the dose profile. And yeah, that's it. Back to the presentation. Okay, so it's back to Anna.
So here, after the demo, we have selected some use cases where OpenTPS has been used. I will talk about the first and the second one, and then Sophie will talk about the third and the fourth. So these examples are not mine, but we have selected because we find it very important. So the first one is about inter and intrafraction motion, mainly. All changes that can happen, but mainly it's for motion management, right? So this is the team of PyLab, and when I mean interfraction, things you can do is translation, rotation, baseline shifts, two more strings, etc. As in the example here, this can be used for data augmentation, robustness evaluation, etc. When I talk about intrafraction changes, then as I said, it's motion, and so we do support 4DCT and modeling of this 4DCT. As for instance, you can use deformation fields with the Morphon algorithm to simulate the mid-position image and the associated contour, which, as you know, it's a better strategy than the regular ITV. And you can do also very exotic things. So you can take the breathing motion signals and apply to different points in your image. And this is what a colleague of us did, Damien. This is also a demo of a very funny thing. So he was using multiple signals on different anatomical points to simulate the breathing motion that is different from one lung to the other. So as you see here in the image on the right, I challenge you to see if you can do that. So you can do many exotic things, and sorry. Oh, yeah. And there has been few papers using this kind of tools of simulating inter and intrafraction motion. I will talk about two papers. The one is this paper here, where they use these tools for data augmentation for a AI model, a convolutional neural network that predicted, so reconstructed a high quality 3D city based on a single X-ray 2D projection. So the idea was to locate the tumor in 3D without the need of implanted markers. And so what they did is to use this data augmentation to generate 500 new synthetic CTs and then train the model on them. And this is in here, you see an example of the ground truth on the left and the predicted. So they claim it is quite good prediction. Another example where you can use these simulations of motion management and stuff is for online treatment guidance. So in here, what they did is to simulate the motion. So you can see here on the right, on the orange dotted line, that's the 4DCT for an example patient. And then on blue is the different scenarios they simulated to anticipate different situations that can happen during the treatment, and then do a treatment plan accordingly and use it for real-time image guidance proton therapy. The second example is from Luciano Rivetti. So I take the opportunity to thank him because he has been doing a great job for adapting OpenTPS functionality to photons, because what we have presented so far is protons, but we would very much like to extend to photons. And Luciano started to do that, and he implemented input and output functions for DICOM plans, RT plans, including VMAT and IMRT, which is very important for the community, of course. And then also he included a photon dose calculation, which is collapse cone convolution. And what is more fancy is that he added classical, but also probabilistic robust optimization for IMRT. And so what it changed here, I'm not going to go into detail, but what it changed in your objective function is that you use a probability map instead of a regular volume for your target volume. And this is also based on this paper from Gregory here. And so example 3.
Yes. So I'm presenting proton arc therapy since my thesis was about proton arc therapy, and actually that's how I dive into OpenTPS by working on optimization for this topic. And so the problem with proton arc therapy is that you have to balance between many different objectives that are conflicting, like in addition to the symmetric one, because now you have much more degree of freedom for your plan, but then at the same time, it means that if you use all of them, the plan will take way too long to deliver in clinical routine. So this is something we want to avoid. So we need to really balance between plan quality, delivery time, and obviously computational resource. So yes, I hear it was to further explain the beam delivery time optimization challenge, comparing an IMPT plan here with 3 beams and a dozen active energy layers in each beam. Then imagine that you decide to convert this plan to partial arc, but keeping the same amount of energy layers in each beam. You will get the so-called multi-field IMPT with 46 beam angle if you use one beam every degree. But then you will get 1,600 active energy layers, which will make the total energy layer switching time very large. So then the challenge in proton arc will be to appropriately select the spots and energy layers such that you minimize your total delivery time while keeping a good plan quality. And so during my thesis, I've tried several different solvers to try to solve the proton arc therapy optimization problem. I've tried with FISTA optimizer, which is sort of gradient descent to which we add regularization. I also tried local surge and simulated annealing, mixed integer programming, and I've everything was done within OpenTPS. I don't think that everything is yet pushed to the master branch, but just to tell you that it enabled my research for my PhD. We have also re-implemented the Spark method from Beaumont Hospital in OpenTPS. And recently, in the last year, we've been working on heuristics to pre-select the energy layers to make it more computationally efficient. And even more recently, we have a PhD student working on adaptive proton arc therapy. He has been presenting at PTCOC this year his work. And here you see the different publication that could be released during my PhD. And then we have also more recently also released conformal flash proton therapy optimization in OpenTPS, but you cannot find it directly on the repo that is online because it's on another repository that you can find. It's still open source, but it's separated. We made it as an extension, a plugin, so that you will have to install first OpenTPS and then also git clone the Flash module, and then you can use everything together. How to use them both at the same time is described on the GitLab. So what it does basically is the optimization of the 3D range modulators for conformal flash proton therapy. But I also know that more recently they have been implementing also a transmission beam into the flash module. So here you can see this is like screenshot from OpenTPS. So you can really see it's nice that we can visualize the range modulator, the collimator, and everything on the GUI. And also on the in 3D, but also on the CT image. And you can obviously also display dose rate distribution, scanning path of the spots, So yes, visualization, as I said, range modulator commutator, dose rate volume histogram, and spot scanning directions. And in short, what has been done in research within the Flash module is this range modulator optimization, but also a very nice feature is that the Flash module incorporates multiple dose rate definitions. So there is the PBS, percentiles. You know that there is a lot of discussion on these definitions. So it's good to have a tool that can compute them, many of them. And this is based on the paper by Sylvain Defay that is referenced here. And there was another research that was done on the scanning pattern optimization to maximize the dose rate using a traveling salesman problem, which is also here reference. And yes, we have many more features in OpenTPS that help us daily in our research program. So we talked about image processing, data augmentation, but for the delivery also. And another important one is beamlet-free optimization, which is kind of hybrid optimization where you do not pre-compute the beamlets. What you do instead is that you will compute the dose and at the same time optimize per batch, like you simulate the dose at the same time as you optimize it, which make it beamlet free and can save some memory usage and computation time. So this has been published last year as a technical note. And yes, we talked about probabilistic planning by Gregory, and yes, adaptive proton arc therapy and other AI applications. So we have a website which is today, I think, in a very good shape. So don't hesitate to visit it. There is also, if you want more practical details, because I stayed, I remained very, let's say, high level still in this presentation. But if you want more details, I encourage you to visit this YouTube video that was the first workshop we gave on OpenTPS, which goes more into the technical details of each feature of OpenTPS. And we show code, we show so comparison of the core and the GUI at the same time to do same things. So yes, that's the website. So here on the website, you can also find some examples that are, I think, updated. Here you also have like a real world example on a brain case. So because like the example on the GitLab is not on the CT because we could not upload the CT on the repository to save some memory, obviously. So here on the website, we show an example of on a real DICOM CT file. And yes, about if you want to use OpenTPS, we strongly advise to close the project so that you can like all the time pull the latest version of the project because it's like still a young project and there are commits. I mean, we try to not a little bit less recently, but we some weeks we make commits every day, and we have an upcoming OpenTPS internal OpenTPS camp where we will try to really push and try to solve many issues that are still there. And if you want to contribute, so yes, the project is hosted on GitLab. So we ask you to fork the project so that you have your own project as a since you are external to the project. And if you want to, like, if you think that you have made a feature of interest, don't hesitate to make a merge request. You won't be able to directly merge because obviously we are trying to protect the master branch. And we have made also some protection on the repository by implementing some unit tests, but they are still not enough. We have to implement more, but just to make sure that the merge request would fail if it does not pass a test, right? And also another maybe advice would be that if you find a bug or solve an issue, I mean, actually, yes, don't hesitate to report a bug and create issue even on a feature request, or if you have written something and you want to discuss, you can create the issue and we can comment on the issue together and see how best we can integrate it to the master branch. And Anna, it's for you.
Yeah, so I thought it would be a good opportunity to also share another initiative we have here in MIRO, and that eventually in the close future, we hope to merge some functionalities with OpenTPS. That's why it's also relevant here. So the platform is called Parrot. It's a platform for artificial intelligence guided radiation oncology treatment, and we do use it for visualization of AI model predictions on contouring and also on the dose. And also we can use it for decision support between protons and photons. So it looks like this. I will not present it in detail, but for you to see that the graphical interface is web-based and is a bit more user-friendly than the current one in OpenTPS. And because it's also web-based, we could connect it to servers too, although today it's a local web application to ensure data privacy. The platform is hosted in Hugging Face, and the AI models are also hosted in Hugging Face, and you can download the latest release in there. And yeah, that's all about Parrot. Then I will finish with the perspective and challenges we have for OpenTPS, but which are also the same as any open source initiative, right? So regarding development and maintenance, our challenge is to have a long-term coding and then having sustainable funding for this kind of tools, because we are in research. It's not always easy to find funding for this kind of projects, which is mainly development and not so much research sometimes, particularly the initial features. Of course, the versioning, and that's also important for Python because the versioning is changing very fast, and then we need to keep track of all the version and libraries, etc. About the community, but some typical challenge that we encounter is that we need to provide more functionalities to the community. And that's why we want to create a new graphical interface to attract more users, clinical profile users, and eventually merge with Parrot. And of course, we need to improve the documentation, and we are thinking about maybe training opportunities in the future. So our perspective today is to have the diffusion of the tool as much as possible. So we presented in PTCOG. We are going to present it also in ICCR next week. And this type of seminars is also within this goal. We want to engage the developer teams and community. That's why we are organizing our first OpenTPS camp for the core team. But I do think we will eventually extend this OpenTPS camp for the rest of users, active users at least. We started to build a community. That's why we have also a discourse group, because GitLab is good for the issues and for the code itself. But when it comes to questions about functionalities and so on, GitLab is not so good. So that's why we are having now a discourse group for this feedback and sharing ideas within the community. We just started 2 months ago or so. What I mentioned about the new graphical interface, this is a project for this end of summer. We do want to work on the graphical interface because we have been working so much on the core that right now it's getting outdated. And we do want to implement all this research from these papers. Sophie mentioned a lot of functionalities from ARC, but also all the work Luciano is doing for Photon should be included in this graphical interface to attract new users from the Photon research. Funding, we are exploring particular grants that are called proof of concept grants, and also we want to collaborate with other open source initiatives. That's why we recently reached out to other people like PyMedFees, PyLinux, and also Matrat, and particularly with Matrat, with Niklas Wall. We had this idea last year to organize an Estro workshop that has been accepted, and we are organizing in few months, and it will be in October. And we have enlarged with another guy from United Kingdom, Joshua Mason, not only for open source software, but anything that has to do with resource sharing in radiotherapy. Like, for instance, sharing commissioning reports, or also sharing scripts from commercial treatment planning system like RayStation and so on. We do believe we don't share enough, and we want to know why, what are the challenges of sharing uh, scripts, softwares, and protocols, etc., and how we can improve that. So if you want to participate, the motivational statement has been extended till the 31st of July. And the outcome of this workshop is to engage in this conversation about open source and resource sharing. But the main outcome, I believe, is to have a registry endorsed by Estro about resources, like I said, scripting, protocol, software, etc. Because we do realize that many people don't know about this, about OpenTPS, and so many tools out there that they can use. And then we want also to establish a sustainable software and resource sharing working group for the future, and work on recommendation on best practices on developing open source and having sustainable software. And I believe that's all. We want to finish by saying that we need you, because open source software without a community is nothing. And so we thank you for your time. And that's our team, and that's our MIRO group. Thank you.
All right. Thank you so much. It was a fantastic presentation, a lot of excellent works by your team. So we do appreciate it on behalf of every researcher in the field. I want to open it up to questions. Please go ahead and ask if there is any questions. I'm going to open up with one. Coming from the optimization, I'm going to start from the optimization part. How actively are you working on including some of the more sort of technical issues with the optimization, such as multi-criteria optimization and inclusion of the DVH metrics, inclusion of more sophisticated optimization based? You mentioned a bit about the extension to Groovy and other off-the-shelf optimization solvers that, just for the people who didn't probably misunderstood, needing the license doesn't mean that you have to pay for it. These softwares have like academic licenses that you can just freely access. So it's not really a hurdle towards using those more sophisticated optimization softwares in OpenTPS. But yes, so wanted to kind of mention, ask with regards to some of the more detailed optimization extensions that might be forthcoming.
Yes, so it's really, let's say, it all depends on the PhD student and their usually project. So it comes by wave. Like I was like really into ProtonArc, and I was just trying out like many different optimization algorithms to try to solve the problem. That's how I came across mixed integer programming, but it was not specifically because it was really for my project at the time. So we don't have this recurrent self-discussion about what, but we should, I think, but it's because we have so many things, everyone at the same time. So, but yeah, I guess it's really about the people and their projects. That's how it happens.
When we manage to hire someone, is usually short term till they start the PhD, things like that. For instance, now we have a contract with someone for 3 months, so it's as Sophie said, it's a wave. So we need to choose one thing and then we implement it, and it's very unstable.
Yeah,
unfortunately.
Very good. And if I may ask a follow-up question, so this Parrot and the OpenTPS, do you see it down the line emerging between the two into one unified platform?
I don't think it will be one unified platform because there are two very different objectives, and that we want to keep the core of the OpenTPS absolutely separated for the people to use scripting and so on. What I see is the graphical interface of Parrot being used, some functionalities like the contouring and so on the AM model for OpenTPS. But we will still keep the two tools separated. Yes, Parrot is a .x that you install and you just run it, and it's ready for users that don't want to code, they just want to look at the images and so on.
So maybe a third platform that has the both functionalities into one.
A third, no.
Yeah.
but the idea also is that like since they are independent, like you could like rebuild your own graphical user interface completely new and use it and call the OpenTPS function. So that's why if we would have this Parrot web-based application, and if we could call OpenTPS function, but we need some sort of translation between the different programming languages, and this is
Parrot
it's
is
not straightforward.
Parrot is JavaScript.
Yeah.
And
okay.
it does have a Python server to call the AI models internally, but all the graphical interface is made on JavaScript.
Got it. All right. Other questions?
I'll jump in with a question. Yeah, thanks for the presentation. It was awesome. I agree with like keeping the tool separate. I think I really appreciate that in like the core versus the GUI and these kinds of things, because like I think it sounds like as long as there's good IO, you can hook up the tool in any which way you want, and you can use other tools, and then what's useful can keep being maintained, and what's not useful can kind of decay as it does with some open source projects. But I guess my kind of main question is, because we've asked it to other open source groups that have presented in this seminar, is what kind of sets your tool apart? Like, is it more that it's familiar for people with a Python background to work with, or like within the open source TPS landscape, why should someone use OpenTPS versus another open source tool?
That's a very good question. I would say first thing is Python. That's why we started a new one. Otherwise, I'm honest, you could use Matrat. It's a very good tool, and it has photons, protons, and even carbon ions, I believe, right? And it's a very complete. But we wanted something in Python. Also,
Very accessible.
Our goal was, because all the lab was using Python, and also because all the AI models are using Python. And we wanted something that could be plugged into these data augmentation tools and maybe calling AI models directly. So that's why we wanted to use OpenTPS. And so first one is Python, second one is MC Square.
Yeah.
Right. But I do believe MC Square, well, Matra has also MC Square, right?
I think it does.
Yeah.
I think it does,
Square,
yes. So I think it's Python what makes different from the others.
Yeah.
Yes.
Yeah.
Cool, thank you.
Also, you can, it's cross-platform usage. Like, you don't have to, I mean, it's the same. It's Python. It can be used on any computer and without any fee. You don't have to,
Yeah, it's free.
Yeah, and I would add, with like any platform on MATLAB is not truly open source. So
Is it? Well, because you need to pay the license.
Yes,
Or-
indeed.
Yeah.
And then there are like some limitations with the access to the internal functionalities of MATLAB and how it
Okay.
handles different aspects. So, all right, other questions? Gregory, please.
Yeah. Yeah. So I mean, great presentation. So I'm a user of OpenTPS, as you mentioned. And yeah, I mean, for my research has been great. So I can endorse from my side. So well, I have a question because in my project, we're exploring, using different types of imaging, like multi-parametric MRI images, and this might affect both the base functions as well as other types of, functions which are built on top. And so, is there any like vision about how to kind of integrate different type of imaging, or like what's the best way to incorporate that into the tool?
We try to make it somehow modular. So you will find an abstract class,
Yeah.
right? So I would say start from the abstract class object.
Yeah,
And
like there is an RT plan, an
yeah.
MR,
Yeah.
a CT. You could have.
No,
an-
because
Yeah,
for instance,
and-
what I saw was like the abstract class is called image 3D, let's say.
yeah.
But then a diffusion weighted image is like a 4D or a 5D image, so and then it becomes a bit, tricky
I mean,
about
you
how
can
to
always build your own data class that then inherits from patient data still.
Yes.
It's also a new file, and
Yeah.
yeah, that's how I would do, I suppose, if you don't find it, let's say, what you want in 3D image.
Yeah. Yeah. Okay. Yeah. Thank you very much.
All right, other questions?
I have one. Again, that's fantastic. So we really appreciate your work and use it a lot, as some of you said. I guess one question I have is, I was impressed that you started with this only in 21, if I understood correctly. So like in a relatively short time, like 3 years, you put it together, and that's very impressive. I'm just curious, how many people were like actually coding, and how did you organize it all? I mean, you must have decided on some strategies together, and so, how did you make those decisions?
Yeah. So Kevin first started alone, right?
Yeah, I think Kevin started in the pandemic.
he had a prototype, and then I arrived, and he put me in charge of this optimization. And then we attracted people like Sylvain arrived from he was working with us, and then now he's working at IBA. And then so it's really like, maybe you can show the slide.
So there was a first prototype by Kevin Sugli
Yeah.
who implemented the main features, and of course we had the knowledge from Meetup and so on, right? So that's why it went a bit
Yes.
faster. And then they did this
we
formatting.
did a refactoring, like we during 1 year we were like 7, I think, at the time. So 1, 2, 3, 4, 5, 6, yeah, 7, 8 people, and we dispatch the task. We decided, okay, you deal with the optimization, you deal with image processing, you deal with input output. So really splitted all the tasks between the 7, 8 of us, and we did this. We met like during a full week, where we would have this agenda every day of like we were working like really like together, and trying to solve issues. And then we had this deadline of release coming up. So we all worked super hard during like 2 months, I think the whole summer at some point. And we
in 2022.
2022, yeah. And then it happened. And now we are responsible for what's out there.
Yeah, fantastic. Congrats again.
Thank you.
I have a question, if I can. I don't know if
Go ahead. Yes,
too late.
yeah.
So yeah, great work. Yeah, I agree with Gregory that OpenTPS is an amazing tool to, to do research and to extend and to try different things in radiation therapy. So I have a question about this is a follow-up question to Thomas. So you show your team, right? I wonder if part of your team are computer scientists or they have a different background. Because when you look at the code, it's very well structured, and it seems like, you know, like it has a whole structure and architecture, which is very difficult to find in scientific codes. You know, we as scientists, we are more disorganized.
No, this comes from Sylvain.
Sylvain does have, it's great for coding.
Yeah, he's actually he's an engineer by training, I think. But he has a strong interest in computing, so he just developed his own skill in it, and together with Kevin also, who was already also very strong in his computing skills. And then once he does that, we follow, because we know how he codes, we know how the code should be structured, and that's how you learn, I suppose, by copying what the others did, and try to understand why we are doing that, because sometimes it's not that clear. Yeah.
Well, thanks.
All right. In the interest of time, unfortunately, we have to come to a conclusion for the meeting, but it was again fantastic talk. Thank you so much. And again, as yet a third approval, or like, you know, a vote of confirmation about the quality of the OpenTPS. We have also been working on it on different projects, and it's really great tool. So for any researchers out there that are thinking of using one tool, certainly take a look at the OpenTPS. And thank you again for this wonderful works that you have been working on since, you know, 3 years ago, or maybe even like approaching 4 years ago. Best of luck in your future, and see you in the ICCR.
Yeah.
Thank you very much for the invitation.
See you. Bye.
Ciao.
Bye.
Bye.